Hello, Mr. Kitchen, Global Skill Richmondville High School Physics. Today we begin our review of waves at the top of page 11 with an introduction to waves. Now we say a wave is a vibratory disturbance that propagates through a medium, but waves transfer energy without transfer of mass. Material waves require a medium in which to propagate. These are things like sound waves, water waves, and so on. The other kind of wave that we can have is an electromagnetic wave, and that can travel through a vacuum. The difference between a pulse and a periodic wave: a pulse is a single vibratory disturbance. The periodic waves is a series of evenly timed pulses. And when a pulse reaches the boundary between two media, part of the pulse is reflected, part of the pulse is absorbed, and the rest of the pulse is transmitted through to the new material. When a pulse is reflected from a fixed end, the pulse is inverted. That is, it's flipped upside down when it hits a fixed end or a boundary. There are two types of wave motion. We start with longitudinal waves. And in longitudinal waves, the particle motion is parallel to the direction of travel. It's made of compressions and rarefactions. And an example of this would be sound waves. Here's our example to the left. This is a representation of a longitudinal wave. We've got compression, rarefaction, compression. The particles are moving side to side. The velocity of the wave is to the right, and we can see these two are parallel to each other. The other type of wave motion that we study are transverse waves, and in this case the particle motion is perpendicular. To the direction of travel. They are made of crests and troughs, and examples of transverse waves would be water waves and electromagnetic waves. Here's our example of a transverse wave made crest, trough, crest. We could see that the particle is moving up and down, the wave is going to the right, so the particle motion is perpendicular to the direction of travel. This line right here in the center is the equilibrium position. Here's some characteristics of periodic waves. Waves are described by their type, longitudinal, transverse, and so on. And these characteristics. Frequency is the number of waves per second, and it's measured in hertz. The symbol for the hertz is capital H, small z. So the hertz is just another name for 1 over seconds, and it can be read as per second. The symbol for frequency that we use is lowercase f for frequency. Period is the time required for one complete wave, so it's measured in seconds. The symbol for the period is t, really represents time, and time is the reciprocal of frequency. And finally we move on to amplitude, or we finish up with amplitude on this page. And amplitude is the maximum displacement from the equilibrium position. And the energy of a wave is proportional to the square of the amplitude. You don't have to know that exact relationship, but understand that as the amplitude gets larger, the energy of the wave gets larger as well. Because the amplitude goes as the square of the energy, if the amplitude doubles, then the energy is going to be 4 times as much. Phase are points on the wave having the same amplitude and direction of impending motion. These are said to be in phase. And here's an example over here. I've got a transverse wave. The velocity is to the right. This point right here has an amplitude above the equilibrium position, a positive amplitude, and it's got a crest coming up next. So the direction of motion of this point is up. The direction of motion of this point is up. They have the same amplitude, so they are one wavelength apart. Similarly, the direction of impending motion of these points are downward, and they are also a wavelength apart. So the wavelength is the distance between successive points in phase, and the symbol for wavelength is the Greek letter lambda. Here's our example of points that are a wavelength apart. The speed of the wave is a product of frequency and wavelength, so v is equal to f times lambda. Here's some periodic wave phenomena that are common to all types of waves. We have wave fronts, and so if we drop a stone into a pond, we get the series of circular wave fronts that are moving outward. So the circles are the wave fronts, and then perpendicular to that, perpendicular symbol here, we have the rays. And the rays show us the direction of the wave. The fronts show us actually the location of the crests of the wave. The Doppler effect, what was that? Well, it was the Doppler effect. It's change in observed frequency due to the relative motion of source and the observer. And if the source and the observer are moving toward each other, the frequency will increase. It causes a change in the pitch of a sound wave. It's going to cause a change in color of a light wave. If the source and the observer are moving toward each other, the frequency will shift toward the blue end of the electromagnetic spectrum. The Doppler effect is used in radar systems, used in all kinds of systems, but Doppler radar can be used to find out not only how far away something is, but how fast it's moving. Interference, well, superposition occurs when two waves pass through each other. Constructive interference occurs when waves are in phase and they're going to add together to form a larger wave. If they're out of phase, they cancel out. Standing waves are formed when two waves of the same amplitude and frequency are traveling in opposite directions. Destructive interference causes nodes to form. Constructive interference causes antinodes to form. And here's our example where we've got a standing wave, and we can show that it's a standing wave because we've got this dotted line over here. So the wave is just oscillating back and forth between these two extreme points. The nodes are the points that are on the equilibrium position. They're the points that don't move. And the antinodes are these points here. They're on the crests of the wave, and they're going to have maximum motion. Resonance is when an object is forced to vibrate at its natural frequency. It will resonate. An example is the Tacoma Narrows Bridge collapse, or we looked at an episode of the Mythbusters where a singer broke glass using the unamplified human voice. We move on to diffraction, and diffraction is the spreading of a wave into the region behind a barrier. Diffraction occurs when the wavelength is large compared to the opening through which it passes. And here's our example of diffraction down here. We've got wave fronts that are coming in. The wavelength is larger than the opening through which they pass, and when they do that, the wave spreads out. We get these circular wave fronts over here. We can see that the rays, which I've drawn in as well, showing the direction of the wave, they're also spreading out. These are the wave fronts that make the circle. So the wave spreads out, and that represents the diffraction. Well, that's where we're going to stop for today at the bottom of page 12. We'll pick up on page 13 next time.